Okay, I think we'll get started. So we'll come back to the harmonic oscillator and look at it in what's called coordinate space. Now we've run into a related but slightly different coordinate space earlier when we were talking about, say, a object that's rotating and then sliding. We have the two dimensions, and we're able to write that as a coordinate space. Here, related, but instead of using two positional coordinates, we're using the position coordinate and the velocity coordinate. This is going to be very closely related to a space that we'll run into after we learn more formally about momentum, where we use position and momentum, and that's called a phase space. So we'll come back to this again after we've gone through momentum. All right, so from last time we saw that the position of the oscillator is cosinusoidal. That's if we have the initial conditions of just pulling back and letting go. Then the velocity is related to that, sinusoidal. Same, A carries along, and then the omega comes out as a multiplier to get the units right. Okay, so if we track these in time, the red here is position, cosinusoidal. Blue is velocity. I've kind of put these on the same graph. Of course, they have different units. This is a position, that's a velocity. But just to show the relationship here, I put them on the same graph. Well, now what we're going to do is take this graph, and we're going to get rid of the time component, and we're going to simply plot what is the velocity and what is the position. And so if I choose this particular time, I have this position and that velocity, and that would go as a point here on this space. So let's start off with where we're at here. We're at x is maximal at A, and then velocity is 0. So that's going to be a point right there. Now, as time goes on a little bit, the system drops in amplitude. So we're going to move in this direction, right? We're going to get lower in value. But we also pick up some velocity, negative velocity, so we're going to head down this way. And so we're going to come off like that. Now, as we continue to go, we will reach the equilibrium point where we are here. Our position is 0, so we're 0, and then maximum negative velocity here. And as we blow right through that, we will start going to negative position, and we will start decreasing our velocity because we'll be decelerating through. Then we'll reach the turning point on the other side and come out of it like that. Back to equilibrium, come out of it like that. And then we finally get back to our original starting point after one period. Well, let's trace how this goes. And we might not take too much to imagine that this will trace out an oval. In general, an oval in the coordinate space. And we can put directions on here if we want to categorize the motion here. And so this is capturing the motion of this in this coordinate space. And so we can see the periodicity very clearly. We can see the turning points very clearly. We can see the maximum and minimum velocities very clearly. So we lose a little bit of information here, but we still capture a lot in this description. And so this is a common thing to do. Let's look at a couple of different cases. Let's say we've got the same harmonic oscillator, but we're going to give it a little more energy or a little less energy. So we'll start with energy E1, and so that means we'll pull it back to an amplitude A1 such that the total energy is 1. So E1 will be 1/2 K A1 squared as total energy. And then E2, we're going to pull it back a little bit further, 1/2 K A2 squared. Well, just like over here, we've got a trajectory that creates an oval in coordinate space. Now we're going to pull back a little bit further, and so we would have another oval. And so as we go with energy, we make concentric ovals in coordinate space. Small oval if we are low in energy, bigger oval if we are high in energy. All right, let's take a different situation. Let's say we've got, we're going to keep the mass the same, but we are going to change the spring out. So we're going to start with a stiff spring, a big force constant, and we're going to go to a looser spring, a smaller force constant. Well, if this is the case, because omega is square root of k over m, then omega 1 will be greater than omega 2, all things equal other than changing the k's. If we pull the system back to the same spot and then let it go, in the case of the smaller omega, we will reach a smaller maximum velocity. And our oval will look like the green one here. If we have a higher omega, then we will reach a bigger maximum velocity, but our turning points will be the same, right? Because I brought it back to the same position. So the shape of the oval changes. We get a little more squeezed oval if our spring constant is weak, and we get a more extended oval in this direction if our spring constant is stronger. All right, so this is coordinate space for the harmonic oscillator. So practice this a little bit. Maybe change the mass, but keep the spring constant the same. Think a lot about how the energy changes the phase diagram. Maybe start with hitting a hammer, hitting it with the hammer. So if we're at equilibrium, we hit with a hammer. That's a different initial condition. Then the x will be sinusoidal, and the velocity will be cosinusoidal. And that just means we should start at a different spot in this oval. But what we'll notice is that the oval is the same. We just start in a different spot on the trajectory here. And so the oval captures the basic behavior and it doesn't really care so much about the initial conditions. All right, and like I say, we'll come back to this when we get to momentum and talk about something called phase space, which will be very quick to get once we feel good about this.